So the class today is on distributed file systems and MapReduce. So we could say that this is the first class of the core of the course where we're looking at modern frameworks for processing and managing lots of data. So the concept of Google file system, which we'll speak about, and MapReduce originates from Google, where they have to deal with massive amounts of data to be able to manage, for example, their web search applications and other applications. So they have to use lots and lots of machines to enable these applications. So they have thousands upon thousands of machines. So distributed computing is integral, it's central to what Google does. And the services it provides, and not just Google, but also Facebook, Twitter, whatever major web application or platform. So speaking about Google, because many of the ideas mentioned in this class originate from Google. So how do they do this, right? So how does Google build its web search next, right? So what processes or algorithms does Google need to implement web search? Any ideas of things that they need to do to implement? Okay, so for example, I'll name first element. We have crawling, right? So what's the idea of crawling? It's this idea of parsing links from web pages, extracting links from those pages and scheduling them for crawling, and then recursively downloading pages in this manner. Right? So this is how they get their hands on the content, on the raw content of web pages, for example. What would come after that? After they have the raw content, what would they need to do?
Identificar qué es lo importante.
And that would come afterwards, yeah. So that would be the third element. Yeah. Well, you could say as well that actually comes now, but how do they enable efficient search? Right? So, when you do a search, it's not that they're going through all the content they've stored locally, right? But rather what they're doing is they are indexing the content. So they're building what are called inverted indexes, which we'll talk about later in the course. But they're parsing keywords from the web pages and then they're indexing, building data structures over those to be able to efficiently find web pages based on keywords. And of course, they have to somehow manage updates and update content of different web pages. And the third thing that was mentioned is figuring out what are the important elements, what are the most important web pages, what are the most important pages for different searches. So ranking involves relevance. How relevant is a page to a search? How important is that page in general? So for example, a Wikipedia article about Barack Obama is probably more important than a tweet about mentioning the same keywords. How many users clicked it and so forth. So we'll also be talking about ranking later in the course. And they have various other processes that they need to implement. So it's quite a complex system. So here we mentioned three main elements. There's also quite a few more elements that they would have to consider. So they have to do this over lots and lots of data, lots and lots of data that are changing, right? So this is quite a technical challenge that they face. So how to implement then all of these processes over lots of different machines? This is the question, right? So we have all these different processes and we'd like to implement them over everything. So if we were to implement every task separately, if I were to assign, for example, one quarter of you to implement the crawling, right, in one team, and a quarter of you to implement the indexing in another team, and a quarter of you to indexing and ranking in another team, and a quarter to implement ... so that we could create a web search engine that would beat Google. And that would seem very inefficient, right? So why do I say that? Because if you were to implement it on top of distributed systems, each team would end up separately having to implement storage, retrieval, distributed processing, communication, fault tolerance, and then they would have to be re-implemented in every separate team. So there are things in common, even though these are very different tasks. There are certain things in common, certain abstractions that would help us at least to work and to implement these different elements on distributed in a distributed setting. So rather than start from scratch, what we'd like to have is some sort of abstraction. So what kinds of abstractions can we have? I mean, the very basic abstraction we could imagine is to be able to write to files, to read from files, to delete files, to append to files in a distributed setting. Right? So this abstraction or this interface here is essentially what is implemented as part of the Google file system. And it has some assumptions that are different from other file systems that we'll see. So what essentially was the idea? This was around 2003, 2004. Google wanted to somehow systematize how it manages data, just files basically, on its thousands of machines. So they proposed this Google file system. So before we answer what is Google file system, we have to answer the question, what is a file system? So what does a file system do? So a file system in general, here I have my file system in Windows. So I have some list of files, some data which are modified, type of the file, the size of the file, and so forth. So this is essentially an interface that you will go over a file system. Or in the command line of Windows, I could use, the command line, and I have another view. I can list the directories and so forth. So a file system, what does it do, right? What services does it provide us? It splits a file up into chunks or blocks or clusters of storage. So it remembers the location and sequence of chunks for our file. So the idea is we want to avoid, for example, some file that's left in the middle blocking either end. So let's say we had a 2 terabyte hard drive here, right? And then we had a file that was 500 megabytes. We wrote that first, and then we wrote one that was 1 gigabyte, okay? And then we delete the 500 megabyte file, right? So now what we have is this 1 gigabyte file sitting in the middle of our 2 gigabyte hard drive. So we have 500 megabytes here and 500 megabytes here, but what happens if, 2 gigabytes, I could say 2 terabytes, but anyways, I'll continue. So 500 megabytes here and 500 megabytes here. So what happens if we want to write a file that's 700 megabytes, for example, large? So essentially, the idea is we don't store files contiguously. We don't store them in this one big chunk although we can, but we don't typically store them or think of files that way. Rather, we think of files as a sequence of chunks or blocks. So I'm not sure if anyone remembers in old computers, they would recommend to defragment your hard drive to try to get files in contiguous storage to somehow put together the data that are often used together to try to speed up a machine. That's not really so common anymore, but this was each of these little squares here is a block of data. I think 64 kilobytes maybe is a typical sort of block size, or 16 kilobytes, depending on the file system. So, okay, aside from splitting up a file into chunks, a file system will also organize files and the directories into a hierarchical structure, like into a tree. So, if you open up your file system, you'll get some sort of hierarchy of different folders and subfolders, and within some of those folders will be files. It tracks some file metadata, for example, the size of the file, the data was created, the last time it was modified, who owns that file, what sorts of permissions are there, 777, 775, 644, read, write, execute, these sorts of permissions. And locks is one editing or using the file at a given point in time. So this is what you can see, maybe right-clicking, for example, you can get some metadata. You can also view the metadata here, for example. It provides read, write, update, delete interfaces. So it provides interfaces for changing or modifying files. Okay. So then the question is, what does Google File System do? We've just spoken about generic file systems. Well, Google File System just does the same thing. It does all of this, but it just happens to do it on thousands upon thousands of machines. So what it provides is an abstraction. An important element of distributed systems is that they provide an abstraction and provides an interface that allows you to do much of what's described here, but in a distributed setting, where essentially the idea is that you won't have to worry about which particular machine stores which chunk of which file, right? It will remember all that for you and abstract that for you. Much in the same way that a file system on your local computer you don't need to worry about what part of the disk precisely the file is on. Okay, so any questions so far? Okay, so which type of architecture do we think that Google uses for the Google file system? Does it use client-peer or does it use peer-to-peer? Yeah, so the answer is it's a bit more complicated. So in the last class, I mentioned that these are kind of abstractions. So what Google does for Google File System is it does have elements that are kind of client server, and it does have elements that are more peer-to-peer. So of course, if you have a massive amount of data, if you have thousands of machines, you don't really want everything going through one machine, right? Because that would just be pointless in a way. But in this sort of case here, it can be very difficult to coordinate which machines should store which data, for example, and which machines are storing which data. So it uses a mix between both. So we could say it's sort of something more like client to peer to peer, server client type architecture. So it doesn't have it doesn't fit clearly into some abstraction. It has elements of both. Okay, so first of all, some things, if we look at the design of Google File System, will look very strange if we don't talk about the assumptions. So the first assumption is that files are huge. So we're typically talking about files that are, gigabytes, maybe even terabytes of size, in size. Files are often read or appended. So the idea is that rather than opening up the text file and editing a couple of words in the middle of it and saving it again, that doesn't happen. We're going to assume that doesn't happen. We're going to assume rather that the files are read from start to finish. And if we want to add something to a file, it's rather going to be stuck at the end. So we're just going to append to the file. Now, Google File System does allow for some changes, but it's not, the system's not optimized for that, right? So concurrency is important, where we might need to read from multiple clients, might need to read data at the same time. Failures are frequent. So even if we're reading a large file, that could take quite a long time. And within that time, one could expect that a failure might happen. Also, streaming is important. So it means that we don't assume, since we have huge files, that we can read the entire file into memory, like into a text editor, into Microsoft Word or something, and then start changing it, and then dump from memory onto the disk when we save. So rather, what we're going to be doing is reading the blocks of the file as a stream. So these are some general assumptions for working with, and it's all basically stems from the first assumption that files are huge. So we have gigabytes or terabytes in our files are gigabytes or terabytes large. So how should Google design its distributed file system, taking that into account, right? So these sorts of assumptions will be important. So let's see. So we'll talk about the design. So the architecture in general, we have 5 chunk servers. And we have essentially each of these chunk servers is a machine that has some storage, has some hard disk. Right? And then we have this master. This somehow controls the state of the Google file system. Okay. So this master keeps in memory some information about the state of the file system. So essentially information about which chunk servers are storing which parts of which files. That's the most important information. So the chunks in this case are 64 megabytes. What this means is if you wrote a file with one word in it and saved it to Google File System, it would take 64 megabytes. It's the smallest unit of storage in Google file system. So it seems ridiculously large, but if we think about it, remember that we assume that files are super big, right? So they're often, gigabytes, terabytes in size. Under that assumption, it seems quite reasonable. Okay, so somehow having the smallest chunk of data being 64 megabytes. By having larger chunks, we have to remember we have fewer chunks to remember, which means that we have fewer chunks to keep track of. The master will have to remember in which location, the locations for fewer chunks. Okay, there's a 64-bit label for each chunk, which identifies it, which is like a key for the chunk. And we're going to assume a replication factor of 3. So this is the typical default replication factor. Why not 2? So what does replication factor mean? First of all, we keep 3 copies of everything. So if something fails, then we have another copy. Why not a replication factor of 2? Well, we can have what are referred to as bisampling faults. These are errors where we have 2 different copies of the data and they disagree with each other. The 2 versions are different. So in that sort of case, it's impossible to fix the error. But if we have a 3rd copy, we can hopefully find a majority, right? So we can hopefully find 2 copies that agree. So 3 copies are useful for these sorts of errors where there are 2 versions that disagree. So we can use the 3rd to break the tie. So we're going to consider pipeline rates. So we have a client, and the client wants to write 150 megabytes of file, include.txt, 150 megabytes, which will occupy 3 chunks, right? 64, 128, and then 22 megabytes in the 3rd chunk, which will still occupy 64 megabytes. How should the client write this? Okay, so the client in this case is a special client for GFS. So the client somehow also has connections not just to the master, but also to the chunk servers. Okay. So how should we do this? How should we manage this write from the client to the GFS? So what would be the simplest? So, okay, if we think about the simplest option, it would be the client sends all the data to the master, right? And then the master figures it out. The master says, okay, I'll divide the file into these chunks, store the chunks on these chunk servers down here. What would be the disadvantage of that? Of just the client sending the data to the master? So it would be that what would happen is essentially if all the clients send all their data through the master, then this master has a lot of traffic. So there's lots of data coming in and going out from the master. But we still need the master somehow to maintain the state of the file system. So what does that mean? It means that we'll need the client will request to write these 3 chunks to the master, and the master will register that request, but the client isn't actually sending the data, just the metadata about the file. So I have this file, it is this size, and then the master sends back some information to the client about which chunk servers should store which blocks of the file. So the master tells the client, hey, this should be stored on A1, C1, and E1, okay? So the first chunk of the file. So the client can then write to any of the chunk servers. It doesn't have to be A1. This order is just arbitrary, right? But the client writes it to any one of those chunk servers. Let's see that again. In this case, it chooses A1, okay? A1 then writes to C1, and then C1 writes to E1. So this avoids any sorts of, it tries to somehow give the machines more or less equal responsibility or equal data traffic. So we're not going through the same machines all the time. Okay. So this is called a pipeline rate. So the same thing happens for the second block. In this case, client writes to B1, B1 writes to A1, A1 to D1, and so forth. So E1, B1, D1 for the third block. And the write is complete. So we have a second file. The client wants to write orange.txt, goes to the master. Master sends back some information about where to store the chunks. and the pipeline write happens again. Okay, does that make sense? So why we're doing this again is we don't want to pass all the data through one machine. So we pass the kind of control, like we pass some metadata with the master to coordinate, but then we do the writes, we pass the actual data directly to the chunk server, to one of the chunk servers that will store the data, and then that will pass it on to its other chunk servers. Any questions? Okay. So I just realized I have no way to tell the time. If it comes close to 3 o'clock, you can maybe tell me. I've left everything outside. You can just put in the chat, or you can tell me like when it's 3 o'clock, so we can take a break. I can't see it when presenting. Okay, so how does essentially the master coordinate with the chunk servers? It is sending messages. How does it ensure fault tolerance? So it sends messages called heartbeats to each of the machines. So it's somehow pinging each machine every so often to see if it's still awake, if it's still working. So if it detects that a machine goes down, for example, C1 fails, what will it do? It will figure out here what C1 was indexing, right? If we go back, if we cheat and go back here, we see it was blue 1 and orange 2. Okay, so it will go to its metadata and we'll find blue 1 and we'll find orange 2. Okay, so what happens then? It figures out, okay, we need another copy of these. We only have 2 copies. So it will assign 2 new replicas here. And it will say, for example, hey, A1 copy blue 1 to B1, and it will say, okay, E1 copy to D1 blue 2. Okay. So it somehow automatically monitors and makes sure that the replication factor is satisfied in the case of failures. Okay, so we'll assume the machine is working here again. The next thing would be reads. So how do we manage if a client is interested in reading the blue dot text file? So the client can send that request to the master, and the master will send back information about which data, which chunk servers store which blocks of data, which chunks of data. And then the client can read from any one of them. Okay. So it can read from blue 1 from A1, blue 2 from D1, blue 3 from E1. Okay. So what about changes within a file? So I said in general that we assume that this is not the case, right? We assume in general that we're not going to change the middle of a file. But if we wanted to, we can. So let's say the client wants to make a change to block 2 of blue.txt, right? So what happens is, for this reason here, I've underlined certain replicas that will be considered the primary replicas. The problem is what happens if there are multiple clients that want to change block 2 of blue.txt at the same time. Or maybe there's another client who is reading blue.txt at the same time that this client is trying to write. It could lead to sort of an inconsistent response. So the master assigns, not all of the replicas are equal, it assigns a primary replica, which is denoted here by underlining. So what happens is each of these primary replicas is in charge of making sure that there's no problems. It somehow manages the locks for the file in the case of writes. So the client tells the master, hey, I want to do this, and the master will return the information about blue.txt. And yeah, so someone's asking to put the microphone closer. So what we can do then, once the client knows which machines store which parts of the data, then they can the client can write directly to one of the machines. So the writing itself is very similar to the pipeline writes before. So how it works afterwards is the request to commit has to go to the primary server, to the primary chunk server for that part. So this is blue.txt. We see that B1 is underlined here. This is the one that controls what happens to that block. So B1, the commit has to go to B1, and then B1 will ask its secondary chunk servers to commit, right? So what this means is essentially B1 is in control of when changes happen to that block. And then B1 will finally acknowledge to the client. So what's interesting here is that we have two different flows. We have the flow for the data, where the data are what are called staged. They're just kind of copied, they're ready on the machine, but nothing is done yet. So the client just can forward to whatever chunk server. And then those chunk servers will do a pipeline, right, in whatever order they see fit. But the control here, like the call to commit to save that change, has to go through the primary replica, the primary chunk server in this case. Okay. Any questions about that? So the overall idea here is that what we want to do is make sure that we don't send too much data through one machine. So, maybe we want to avoid sending lots of data through the master, for example, but also through the primary replica. So we can transfer the data however we want. But we do need to have one machine that's keeping track of who has the lock or what's happening with this block of data. And we just send the metadata that are needed again through that machine. Okay, so it doesn't become a bottleneck. Okay, so nearly there for Google File System. Yes, so this would be to avoid the master. It would also be to avoid maybe if there were a replica, a primary chunk server of a chunk that was very often written to or changed or deleted or moved or somehow appended to or replaced. If there was a primary chunk server of a chunk that was often replaced then or rewritten, then you would want to avoid sending the data there to that machine and having it also forwarded. So it's somehow by being more flexible about how we share the data, we can balance how the traffic in the networks, because of course the data themselves are much larger than the metadata, like the commits and acknowledgements. So for sure, we want to avoid the master, but in this case, we don't even have to send the data to the primary chunk server. We can send it to any server, which allows us to balance the traffic a bit better. Only the control data, only the metadata goes through the primary chunk server. Okay, so we avoid bottlenecks essentially. So another element that we can consider is rack awareness. So what is a rack, first of all? A rack is essentially a cabinet, we could say, a vertical kind of collection of machines like this. And these racks have switches at the level of each rack, which somehow interconnects the machines on that rack. Okay, so we have 1, 2, we can see 3 racks here. So more or less, how does the networking work? Each rack has a switch, which connects the machines here. We have 3 rack switches here, 3 racks with 3 different switches. And then we have core switches. So 1 or more core switches. And the cores then connect the different racks. So here's the issue. What happens if a rack switch fails, right? We could have 3 copies in this of our block and in this rack and the 3 machines in this rack. And then we have trouble, right? Because we cannot access that block anymore while this rack switch is down. So the idea of rack awareness is to avoid losing data because of a rack switch. So what we can do is rather store data using rack awareness. And how this is typically done is we have to tell the master about which machines are on which racks. So you might have seen before I had A1, B1, C1, D1, Y1, right? So 1 was the rack. So in this case, we have, rack A switch, 1, 2, 3, 4, 5, and we have rack B switch, 1, 2, 3, 4, 5. So we tell the master about which machines are on which racks, and it will then assign the data so that we never have all of the blocks, all of the chunks on one rack. Okay. So the typical way to do this is to put 2 copies on one rack and 1 copy elsewhere. This is seen as a good balance. So why 2 copies on 1 rack? It's easier for one machine to forward. We reduce the load on the core switch. So if we just have 2 copies on the 1 rack, it means that
the machine from one rack can forward to another machine on another rack in the pipeline right more easily than across the core switch. Okay, but we have copies of 2 copies of everything, or we have at least 2 racks with a replica of each chunk. Any questions about that? Or okay, so we have some other operations that I won't talk about in too much detail. We have a rebalancing that will, if it detects that the storage is becoming unbalanced and there's a lot of data ending up in chunk server, or if a new machine joins, the idea is to spread the storage out more evenly. We also have deletions. So how this works is you just rename the file with a hidden file name, just stick a suffix like a del onto the end or whatever you want to do. And then you can recover that from the recycle bin, let's say, by renaming it back, removing the suffix or whatever, and then periodically deleting all the files using a cleanup. There's also a possibility that a chunk server goes down and then some changes are made to some of the blocks that it had, and then it comes back up, right? So you somehow want to, consider the chunk server again. You don't want to completely exclude it, nor do you want to completely delete all the data it had. But there is a danger that it might reappear with an old version of something that might cause problems. So the master has to monitor some of the versions and when things were changed or edited last to make sure that a chunk server doesn't come back with some old data. Okay, I think it must be about 3 o'clock. I'm not sure. Yeah, okay, it's 3:03. So we can take a break for 10 minutes. So let's say from 3:05 to 3:15. Any questions about this?
Profe,
Yep.
cuando cae un rack o un server y se replican en otro, después y ese server después vuelve, o ese rack vuelve, ¿hay algún daemon después que borra las réplicas que se hicieron?
So in that case, the master would have to decide somehow whether or not to keep the copies that machine that came back has. What's common? So it's a good question, but it's quite a complex question. So first of all, it depends on how long the machine was down for. So it could happen that something goes down for a second or a couple of seconds, and it's not actually possible to reassign all of the chunks of that server to be able to satisfy the replication factor. So in that case, it will try to somehow recover. It will try to just to continue using that chunk server again once it comes back up. So in the case that it's been down for a while, it might have reassigned all of the chunks to different machines, to different chunk servers. In which case, what will happen is rather probably the chunk server, the chunks would be white essentially, and there would be a rebalancing to take place because now we have 4 copies of everything, right? So it might not make a whole lot of sense to just keep the 4th copy of those chunks there. So it would be a mix between rebalancing and using the data that's already on the server. But the main thing here is that all of that depends on knowing whether or not something changed. So you need to know when the machine comes up, which chunk is valid and which one is not. And this is what the version info helps with. It helps to know which chunks you could conceivably keep on that machine when you're doing rebalancing, or if you want to try to satisfy the replication factor. So it helps you decide, okay, I can keep these chunks. Maybe I don't want to anymore because I have 3 copies elsewhere, but I could keep these and maybe I could copy some of the other chunks to other machines. So does that make sense?
Depende.
So it depends. Yeah, exactly. So what is particularly important, and it's good to mention, I think, is just that there are different ways a machine could go down. And often these distributed systems will kind of have a different way for handling short errors or more long-term errors. So if it's a short error of a couple of seconds, it will try to survive rather than reassigning everything. But it might not know beforehand, of course. So, but yeah. Okay, more questions or doubts? Okay, so see you at 3:15. Okay, so chat over here. Chat has disappeared. Stop share. Screen. Nope. I'm trying to get the chat to appear while I'm presenting, but it seems complicated. I can only see. Okay, we'll continue. I can see. I can try later to get the chat again. So, what are the main weaknesses of Google File System? Any ideas? So, what would you say is the main weaknesses of this architecture we've seen? So one thing that seems to be possibly an issue will be the master, right? So we have a single point of failure. So if we skip forward, the master node is a single point of failure. So we can try to address that by using hardware replication, which means that we have two machines doing exactly the same thing. We can try to use logs and checkpoints to at least make sure that if the machine goes down, because we have the state of the Google file system in memory, that we can replay it from a log or a checkpoint to bring it back up. It's also a bottleneck, so we could try to use a more powerful machine. And we can also try to minimize master node traffic, which we've seen. So we try to do pipeline reads and writes. So direct reads, sorry, and pipeline writes. So we don't send all of the data in the Google file system through the master node. So the data needs to be kept in memory. So each chunk needs 64 bytes to address at least. So this puts a limit as well on the scale of the distributed file system, the Google file system, because if we have limited memory on the master node, then we have a limited number of chunks we can store. However, remembering that every block has 64 megabytes and we only need 64 bytes to address, we can think that roughly speaking, we can store 1 million times more data on disk than the capacity of the master node in memory, roughly speaking, right? So that's a huge amount of data. So in general, because the chunks are so big, we can still, with a small amount of memory on the master, store a lot of data in the Google file system on disk. Okay, so in terms of Google file system, that was a proprietary system, but there has been an open source version of it called Hadoop Distributed File System, HDFS, which has been released, which is just an open source implementation of precisely the same ideas that we've seen. So in general, there's some differences in names. So a data node in HDFS is a chunk server, and a name node in HDFS is a master. So in HDFS, we call them data nodes and name nodes. It's again the same idea. It's essentially an implementation of the Google white paper. The main difference being that HDFS is open source. It's an Apache project, and it's quite popularly used in practice. It's still, very popular in practice to store lots of data on HDFS over multiple machines. So, okay, so what we've managed to do is essentially simplify some of these tasks, implementing some of these tasks by at least having a distributed abstraction for managing and modifying files. So this is essentially the abstraction that HDFS or GFS provides us. So are we done? Is this all we need? Well, really all we've done is implement a very a quite basic version of a file system, right? So we've not actually, given any abstractions for building applications for processing data, for example. So it's a useful abstraction, but maybe we can build other abstractions, more high-level abstractions to help us with common sorts of tasks. And that introduces us to MapReduce, which was again proposed in a Google setting. Any questions first? Okay, so MapReduce again was proposed by Google. This was in 2004. So it's a abstraction for processing large amounts of data over large amounts of machines. And it follows a lot of the principles that we saw in the first class, okay? Which is it will use the disk and it will use sorting. It will use a lot of sorting. So, okay, let's forget about MapReduce for a second and think about distributed processing. So here's you. And you have assigned to you 4 workers that can help you, okay? So 4 colleagues in the class, for example. So you form a sort of distributed system, right? What's your task? Your task is you're given a lot of playing cards, thousands of playing cards that are all mixed in a jumble. And the expected output of the task is to provide a count of precisely how many there is of each type of card, right? So how would you do this? What would be the most efficient way? So you receive all the cards at the start, but you have people who can help you. Here are 4, we could say N people. And your goal would be to output as quickly as possible as a team the counts of how many of these individual cards there are. Any ideas on how you would go about this? Okay, so we could make, yep.
Maybe I would split the whole of the cards into 5 sections. So each of us will sort the cards in each of the piles.
So you would take the cards and split them kind of more or less randomly, but in whatever order they're given to you, and split them into 5 chunks and then assign the 5 to each. And then each sorts, and the last part would be then one issue is that everyone would have, if you ask everyone to count their own chunk, then the problem at the end is that you'll have to merge the counts. So for each of the 52 values, then you would have to go across all 5 and you would have to merge the counts. So it's a very valid, probably in practice, it might even be the fastest. Is there another option maybe? So there is another option where either you start with this, maybe it might even be better. You start by separating the cards into 5. And then you all assign different suits or different types of cards to each worker. So that, for example, okay, let's simplify it and assume that you're not going to do any of the work, right? You're just there to coordinate. So you could give all the hearts to worker 1, all the diamonds go to worker 2, all of the spades go to worker 3, and all of the clubs go to worker 4, for example. Or you could just split them up at the start, and then they pass each other the cards, so that all the hearts end up at worker 1, all the diamonds end up at worker 2, the clubs and the spades and worker 3 and 4. And then they can independently sort or count, and they will have the final count, right? So there will be no need to merge the counts at the end. Okay. So maybe that second one might be faster. It depends on how fast or slow you think you can do the merge, right? Given that there's only 52 different types of cards, it might not be that bad. It would be interesting to try this experiment to see which is faster in the class sometime. But, okay, so we have different options. So, okay, thinking about it's a similar problem, but where we have a lot more unique values, right? Not just 52. How could we do a distributed word count? So one option would be to count. A lot of noise. I'm not sure how loud that is here or for you. So one option would be to count the parts in memory on different machines and merge, right? So we could just break up the file and give parts of the file to different machines, and every machine does a count in memory, for example, which we know to be very efficient. And then later we worry about merging all of the counts, right? So then what happens, we could ask if the data don't fit in memory on each of the machines. And how do we also do that merge? So how are we going to, sum the counts for these words or these phrases across the different machines afterwards? So another idea would be to count parts on disk on different machines and merge, right? So rather than doing it in memory, we just do the count on disk like we saw with the sorting in the first class. But we're still left with this problem of how to do the merge, what machine should do it, how we organize the merge across the different machines, because what we want to do is sum for each word that counts on the different machines, and that doesn't seem to be a trivial problem to resolve. So how we'll do it is a bit different. So we have an input where we assume that we have a file on the distributed file system. So magically, in a way, we have different chunk servers with different chunks of the file, right? So it's already split up across the different workers. What these machines are going to do is they're going to partition the words in the file. So they're going to send all the words that start with a letter between A and K to A1, between L and Q to B1, and between R and Z or R and Z to C1. Okay. So then each of these machines can do a distributed sort or count. So in parallel, they can count the occurrences of the words and they can produce an output. And what's nice about this way of doing it is that this output is the final output, right? Split over all the machines. So it means we don't have to merge afterwards. If we partition beforehand, we won't have to merge the counts at the end. So this is more or less the idea. This is similar to what MapReduce, how MapReduce sees this sort of distributed processing. Is there a better method of partitioning that we could use rather than to say all the words between A and K go here, all the words between L and Q go here? Is there maybe a neater way so we don't have to define these sorts of ranges? So what we can do is, randomly assign words, but then how do we know, which words we randomly assign to which machine? But we could use this function here, which would be to hash the word, which produces an integer, and then do modulo m. So what does modulo m do? It returns the remainder when we divide by that number. So let's say, for example, we hash the word and we get 23, and then we do modulo 5, we would get 3, and then we could assign that to the third machine or the fourth machine, depending on however the mod is defined. So, okay, this is the general idea. This is how we would do something like a word count. Now, MapReduce is not just for counting words, but we'll get to that. So, under the hood, what is MapReduce doing more specifically? So there are 7 stages, 7 phases of MapReduce. So there is the input, which is typically from the distributed file system, from HDFS in particular, if this is, okay. From the distributed file system, I'm getting ahead of myself. So the chunks of the files are already split up over the different machines. So these nodes here are just different machines. This is machine 1, this is machine 2, and this is machine 3. There is then a map process, which effectively defines which items go to which machine. Okay, so here we have 3 different machines: green, cyan, and magenta. So we have all the green sort of items will end up on one machine, all the cyan will end up on another, and all the magenta will end up on a third machine. And then these locally work on their kind of partition of the data, their items, and they apply what's called the reducing process to produce the output. So we have 7 steps: input, map, partition, shuffle. This is where essentially all the items get shared to the respective machine. Merge sort, reduce, and output. And I'm going to give a more detailed example of this, these stages. So let's say we have to do a word count where we have this file here. And of course, our files would be much larger in practice, but this is our file, and we can assume that it's broken up into 3 chunks in the distributed file system. So what MapReduce will do is it will read in input from the file, which would be an offset of what position of the file we're reading from, and it reads line by line from the file. Okay, so we assume that we read 1 line on each of the machines. We could read several lines on each machine. So we're going to first of all map. So we read in this input, and what we have to do is break down the lines into words. So what we're going to do is we're going to create key value pairs where our keys are words and our values are just ones for the moment. Okay, so this will become clear why we just add these ones here. It wouldn't be entirely necessary, but we always need to produce key value pairs, so we need some sort of value here. So we just break down the line into key value pairs, in this case 3 key value pairs. After that, we apply a partition and a sort, right? So what we are doing essentially is we are assigning, first of all, we're doing 2 things. We're splitting these key value pairs into machines that they will end up with using a hash modulo on the word. Okay, so we assign different pairs to different machines, and we sort those blocks. So essentially, we're doing a merge sort where we're in memory, we're sorting the data that's going to go to each machine. And when our memory fills up, we just write a block. So we could send multiple blocks to the same machine. So we're doing a sort of in-memory partition and count, and then we write the batches to the disk. And in the next step, these will get shared. These batches of sorted key value pairs will get shuffled, sent to the machine on which they should reside. The important thing here being that every machine, for example, word K, appears in all 3 machines here, but all of the pairs will end up on the single machine here. So all of these batches are sorted. So what we can do then is a merge sort. So like we saw in the first class. So doing a merge sort, we can somehow get a stream and iterator over the full sorted data, right? Over all the sorted pairs for that machine. And then we can apply a reduce, which is a function that just tells us what to do. So essentially for the reduce, we get passed a key, and all of the values associated with that key. So we'll have an iterator over all the values. So this then will allow us to define a reduction, which will, for example, in this case, we'll just sum all the values for every key, and that produces our output here. Okay, so in the case of K, 1, 1, 1, 1 here, we apply a sum and we get K4, for example. In the case of Z, 1, 1, we apply a sum and we get Z2. And this is then our output, right? So we can write this to the distributed file system again, and we're done. So these are the different phases, right? So again, it's based on a similar principle to what we saw on disk in the first class, just that we're doing it in a distributed setting, and we have this shuffle phase here, where we assign different key value pairs to different machines based on their key, right? Any questions?
Profe, la parte del shuffle, no entendí cómo se asignaba.
Yep. So the shuffle here, like it decides that this will stay on the blue machine because it will take the string Z. It will apply a hash on that, which will produce an integer,
Okay.
and then it will do modulo 3. Yeah.
Yeah, genial.
Any other questions? Okay, so this is quite important, let's say, this concept. Okay, so if it's clear, there is another element which is optional, which is called a combiner, and it's essentially a way to optimize this process. So how the combiner works? Okay, let's go back and look at something that's a bit inefficient here. If we look at this aspect here, if we look at this process, we see that we have K1. If we imagine we had a very popular word like de or something that appears many times in a file, In this process, we would have the1, 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 right? And this is sorted, so it's sort of, it seems a waste. Why wouldn't you just write the5, or in this case, K2, right? So if you did that, then you would have to send less data across the network. Remember that this is all over the network, right? Because you need to change data between machines. So rather than write K1 twice, right? Why not write K2, right? So this is an optimization called the combiner. And it's sort of like a map side reduction. So we'll see how that works. So we have our partition here, and we've sorted each of the batches that we're going to send to each individual machine. But before we write the batch, as we're sorting it and partitioning, we can call a combiner. And essentially what that will do is apply a reduction at this phase here before we write the batch to the disk. So we can say, okay, as we're producing these pairs for each machine, what we can do is just sum the ones. Yeah. So it's not the case that this will be the final value or the final count, but it will just reduce somehow some of the inputs that we have. So, and then the rest of the process is the same. We have K2 here, we have K2 here, we have K112 here, and then we get the same output because when you sum, the sum of the sums will be on the same value, right? So we can do this when we have operations that are commutative and associative, where the order doesn't matter in which order we apply things. And we can apply them in a nested way, let's say. So for example, with sum it works. With average, it wouldn't work. If we were taking the average of all these values at the end, we couldn't average some values and then average other ones later because the result would be different. Okay. So for sum, it works. For a product, for the multiplying numbers, it would work, for example. For an average, it wouldn't work. So sometimes we can do this and sometimes we can't. Okay. So this is the option of a combiner. So what's the benefit of the combiner? It reduces the amount of data that we're going to shuffle over the network. And in this case, it would be super useful because there are words that appear very commonly. And rather than writing the1, 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 and sending that over the network, we can just send the with however many times it appears in that batch of data that we're processing. Okay. Any questions, doubts about that? Okay, so we can just briefly talk about how it works for more complex tasks, right? So we'll take a more realistic example that's not just counting words. So we're working in a supermarket, for example, and our boss wants to know, do we sell more in the morning hours or the evening hours? And he or she is interested also in like, what products are we selling more? Are we selling more coffee in the mornings? Are we selling more coffee in the evening hours? And this sort of information. So what they want essentially is a count of how much of each product is being sold, or a count of the total products that are being sold in the morning after hours and the evening after hours. So actually in this case, sorry, the example isn't by item, it's just a total account. So it's how much are you selling at each hour in total, right? So what do you have as input? You have a very large, maybe CSV or TSV file, something like that, with all the purchases, where you have a receipt ID and an item ID. So what items are sold and what receipts. You have a time where your receipt was issued. So this is, you know, what time a purchase was made. These are the items in the purchase. And then you have a separate data file, which gives for each item its name and its price. Okay. So you have three huge files, could be terabytes or gigabytes. I won't say petabytes, but could be terabytes large each file, for example, and you want to produce this sum here. So how do you do this in MapReduce? So, okay, what we have here is sort of a pseudo code, a way of kind of describing tasks on a high level. So what we can do is we can have multiple maps that feed into the same reduce. So this map here is purchase. It takes as input the purchase file, the purchase table. We have a second map that inputs the time. And in a relational algebra setting or in an SQL setting, what we want to do is a join on receipt ID, right? So we can do something, we can do the same thing in MapReduce. We can do joins. So what we're going to do is we're going to use the same key in this map as in this map, which would be the receipt ID. So when we do this, the MapReduce framework will use this to partition. We'll use the receipt ID to partition both the purchase tuples and the time tuples and assign the same receipt ID to the same machine. And then it will automatically give each machine a sequence of, for each key, it will give all of the values associated for that. So in the reduce, we'll have the receipt ID, we'll have a list of multiple items, and we'll have an hour. Okay, so for each receipt, we'll receive this information. And what do we want to output then? We want to output the time at which each item was bought. We're not interested in the receipt ID. All we want to get from this is this item was sold at this time. Okay, so in the second task, we take the output from this, and what we're going to do is join it with item. So we know at what time the items were bought, and now we want to join the item ID where we have the time. We want to join it with the price from this table. So we take the input from this process here, we take the item table, we join them by using the same item ID, okay? And then for each item, we'll have all of the hours and the price. And what we want to output then is the hour and the price here. So for each hour, which could be maybe the time, or it could be the specific hour, right? We don't really care about the specific time. So 1900 just becomes 19, 1859 becomes 18. So for each hour, we have a list of the price of something that was sold, which can include duplicates as well. You know, if we sell the same item or two items with the same price, that pair might appear multiple times. The last thing we want to do is we just take this output here, which has all the prices and the hours that that price was paid. We take all of those and we map by hour, okay, which will become the key. And then in our reduction, we'll have for each hour the price, a list of all the prices of things that were sold. And we can just sum those prices in our reduction. And that gives us our output, which would be the sales per hour. So this is one way to do it. So we could, what we've done in a relational sense here is join purchase with time. Then we joined item with that, okay? And then we've applied a sort of a group by hour and a sum. So we can express these sorts of these queries, and we can run them as MapReduce jobs, though we'll have to code the map and reduce jobs. I think I'm out of time, am I? I am. Okay. So any questions or doubts about that? No? Okay. So essentially, maybe just to wrap up this section very briefly, we now have this new distributed abstraction, which is this MapReduce framework. In the MapReduce framework, I'll talk about this a little bit more in the second part, but all we have to define is a map function, a reduce function, what is our input and what is our output. So map says which key values should go to which machine, and the reduce says, given a key, how should I reduce all of its values to the output? So it takes care of the low-level implementation. It gives somehow, it abstracts away the details of the machines. It provides fault tolerance for you, abstracts physical locations and so forth. So the programmers then have time for more important things. So a lot of the work is already done for them. Yeah. So I'll talk about the next part at the start of the class. What I'd like to just discuss, this is the sort of MapReduce framework you've seen. I'm going to discuss the Hadoop, which is the open source implementation of that in Java. Yep, so any questions or doubts? Okay, I see in the chat there was some comments. I couldn't see the chat. I have to figure out how to get sometimes it appears and sometimes when I try to open it while I'm presenting it doesn't appear. So let me revise. There's a bottleneck in the master. Yeah. Also the single point of failure. The partition is based on the hash of the word with the modulo modulo the sort of divisor remainder of the division. Yeah, so I couldn't see it in the second half of the chat. I have to figure out, because sometimes if I'm presenting, if I try to open the chat, it's just somewhere else. I can't see it. I'll try to resolve that. Okay, see you in the class in the lab on Wednesday. You'll have we'll have a lab with Hadoop where you'll implement a data processing task on MapReduce. Any last questions or comments? Okay, then see you on Wednesday. Yeah, the slides are already up. They're not the video, obviously, but the slides are on the homepage. Yeah. Okay, see you on Wednesday.